Okay, thank you. So good snowy morning to everybody. Thank you for attending today's CGD seminar. This morning's speaker is Cara Nissen from University of Colorado at Boulder. Cara will be presenting on abruptly attenuated carbon sequestration with Weddell Sea dense waters by 2100. Cara is currently a postdoc fellow in Nikki Lewandowski's Ocean Biogeochemistry Group in the Institute of Arctic and Alpine Research, or INSTAR, at University of Colorado Boulder. And she just started her position a couple of months ago in September of 2022. So Cara holds a PhD from ETH Zurich, an MS from University of Bergen in Norway, as well as a BS from University of Kiel in Germany. Her research focuses on the modeling of the Southern Ocean carbon and nutrient cycles under present and future climates, focusing on how ocean circulation, the cryosphere, and the ocean biosphere biology interact to shape the high latitude biogeochemistry cycles. She has several recent papers published on these topics, including the one today's presentation is based on, which recently appeared in Nature Communications. And she's also published on the competition between Phaeocystis and diatoms, as well as plankton community structures in the Southern Ocean. And as we have done today with previous, as we will do today, as we've done with previous seminars, sorry, that made no sense. If you are online, you can submit questions for the speaker to address at the end of our talk by going to Slido and then inputting the hashtag for our page, which is simply CGD seminar. Thank you.
Thanks so much. Thanks, Monica, for the introduction, and thank you for the opportunity to present my recent work here today. I want to thank you all for coming in today. It's a much bigger audience than I anticipated with this weather, and hi also to the online viewers. So as Monica said, I'm going to present on a paper that was recently published entitled Abruptly Attenuated Carbon Sequestration with Weddell Sea Dense Waters by 2100. And this is the result of what I call my pandemic postdoc that I've done at the Alfred Wegener Institute between beginning of 2020 and this summer, before moving here in collaboration with only Avi folks, so Ralf Timmermann, Mario Hoppema, Özgür Gürses, and Judith Haug. And as was already mentioned, this is has recently been published in Nature Communications, so you're welcome to check that out if you want more details or come talk to me after the talk. So I'm going to take you into the high latitude Southern Ocean today, more in particular the Weddell Sea in this high latitude South Atlantic. But what you see here on this map is a depiction of where we think, or we know as of today, where Antarctic bottom water, or the precursors of Antarctic bottom water, are formed in the high latitude Southern Ocean. And on the right, you see a depiction of what our historical evolution of knowledge is with respect to the importance of the different dense water formation sites to the total volume of bottom water formed in the high latitudes. And you can see the Weddell Sea in red. I'm not sure if the online, they can probably see my cursor, right? Yeah. The Weddell Sea was the first being discovered, so that's why they've always had a high importance up on that graph. But then they've sustained their high importance over time, even as other dense water formation sites have been discovered over time. The Weddell Sea still today is considered the most important dense water formation site in the high latitude Southern Ocean. And when I zoom in and give you a bit of an overview of the important circulation features in the area of interest, this is sketched here on top of the bottom topography in the back. So you see there's a clear distinction between the continental shelf area in the southern part and then the more open ocean area in further north, or the central Weddell Sea. And the circulation is dominated by the cyclonic gyre that causes the upwelling in the central Weddell Sea. And then at the same time, we have the overflows of dense waters that leave the continental shelves in two distinct regions, namely in the northwestern part of the Weddell Sea. But the most important region is the so-called Filchner Trough, which you will hear reappear throughout my talk today. So in the context of my talk, I'm mostly interested in carbon cycling. So dense water formation regions do not only matter to the physical oceanographers, but also to the biogeochemists, because dense water formation regions, as I've described, the dense shelf waters, as they descend into the deep ocean, they do not only transport physical properties, but of course also carbon into the deep ocean. And so as biogeochemists, we're naturally interested in this region as well, because this is the region where the carbon can then be locked away from interactions with the atmosphere on very long centennial to sometimes millennial timescales. So in the Weddell Sea in particular, there's the precursors that are formed there are the dense shelf water on the shelf, which, as I said, descends the continental slope into the deep ocean and thereby forms either Weddell Sea deep or Weddell Sea bottom water, which ultimately make up the Weddell Sea's contribution to Antarctic bottom water globally. And it's important to note that the formation of these water masses happens on the continental shelves via water mass transformations. So that means via the ice ocean, and here I also mean sea ice ocean and ice shelf ocean interactions, as well as atmosphere ocean interactions. So their formation really happens in the highest latitudes and not in the open ocean out here. And so one outstanding question before my work really was whether these dense water formation regions will continue to efficiently sequester carbon, so transport the carbon from the continental shelves into the deep ocean under ongoing climate change. There has been some previous work on this general topic when we only focus on the physical part of this, so how Antarctic bottom water formation will respond to climate change. And previous studies have suggested that there might be a pronounced decline or even a complete shutdown of Southern Ocean dense water formation over the 21st century. I want to put a big however behind that statement, though, because the models that were used, and you are all very familiar with these types of models, the models that were used in these assessments were CMIP-type models. And what I show here, and there's a couple of shortcomings that I will point out to you in the following. So what you see here is a bottom density bias. It doesn't even matter which models are shown, it's just four models that I've picked here from the CMIP-6 suite of models for the historical period. And what I want to point out to you is the black contour here in the Weddell Sea. So I've picked four models that have an extraordinarily large winter mixed layer in most of the Weddell Sea, just illustrating that these models are convective, so-called convective models, so they form their Antarctic bottom water via deep convection in the Weddell Sea. And it is important to note, I only show four here. CSM is not part of these four, I checked. It's 24 out of the 35 models assessed in this study by Jose that show the deep convection, and 19 of these have the most years. And that is just not what we think to know based on observations. This widespread deep ocean convection is just not realistic. So I have to say this is clearly an improvement to CMIP-5. There's been studies on that, but it's still the majority of the CMIP models to still get the formation processes of Antarctic bottom water incorrect. And of course, that has consequences as we move or use these models to project future climates or the future evolution of Antarctic bottom water. And I would say the fact that they do not form their bottom water via the right mechanisms clearly adds an uncertainty to the associated future projections in these particular regions. So recently, last year, there's been a study by Lockwood et al. Who looked at the effect of model resolution on this topic. So what you see here in these two bottom plots, let's just look at the whole Southern Ocean one. They generally show the same thing. In red, you see the CMIP-5 multi-model ensemble mean of a normalized convection area. So let's think of it as just the strength of open ocean deep convection and how this evolves as we move into the future. And what we see here in the red line is this aforementioned decline, and in some models even shutdown of the convection as we move into the future. But then we have this blue line, which is one of these convective models, in this case the GFDL model, run at a much higher resolution. And what they found in this model is that if you increase the model resolution at the high latitudes, this response to the ongoing climate change, namely this reduction, does not take place anymore. You have similar deep convection events at the very end of their simulation as you have at the beginning. So really, the response to ongoing climate change seems to be very much dependent on how high latitude processes are represented. And in particular, in their study, they argued that these differences between the CMIP-5 or CMIP-6 type models and their high resolution climate model that they've tested here are related to how the changes in the coastal buoyancy forcing, so the freshwater heat forcing that is imposed on the ocean under climate change, how that is then communicated to the open ocean. And that has a lot to do with how the Antarctic slope front is represented in that area, so really acting as a barrier for communication of changes along the coast to the open ocean. So really, to summarize, the shortcomings here is most of these models, not all, are very coarse in grid resolution on the continental shelves. And as a consequence, they almost cannot correctly represent the processes that are important in dense water formation. And most of them, if not all, I haven't checked every single one, do not include ocean ice shelf interactions at all, or if they do, only very crudely. And of course, in the context of my study, there's no talk about carbon in any of this at all. So this is really where my study comes in. So we use the global model FESOM 1.4. It's the in-house physical model at the Alfred Wegener Institute that has a representation of ice shelf cavities. We coupled this to the biogeochemical model RECOM 2, and we run our simulations on a mesh with an elevated grid resolution in the southern Weddell Sea, so the focus region of our study. So you see here just to depict like a picture of the grid resolution in the focus area, and you see we go down to just 3 kilometers in the ice shelf cavities. And it's important to know this is eddy permitting. This is still not eddy resolving at these latitudes, but still, I think, a huge step forward compared to other setups available. I marked here the transect SR4 because that's just the limit of my focus region. So you'll hear me talk about the southern Weddell Sea, and I'm referring to the areas south of this transect, so really high latitudes. I've run a couple of simulations for this study. They all run from 1950 to 2100. So these are ocean-only simulations, so just ocean physics, the ice compartment, and biogeochemistry. And they're forced with atmospheric output from the CMIP6 contribution of the AVI climate model. And what I'll show here is just the historical forcing and the SSP 585, so a very high emission scenario. And I have two setups. The first one, which I call simulation A, is the one with varying climate and increasing CO2. And then two kind of sensitivity cases where in one case, simulation C, I hold the climate constant at 1950s levels and just let atmospheric CO2 increase. And then the third one where I keep both constant as kind of a control simulation. So if we jump right into the first part of the results, I'll now talk about the deep ocean carbon inventory in the southern Weddell Sea. And again, southern Weddell Sea means, as I depict up here, the area south of this transect. And when I say deep, I refer to the ocean volume below 2,000 meters. So this is the evolution of carbon accumulation, or the accumulated carbon over time in this deep ocean volume in the southern Weddell Sea. And we see that there is 0.75 petagrams accumulating overall. And just to put this in context to the atmospheric or the oceanic CO2 uptake in the area around over the same time, this amounts to 26%. So 26 of the carbon taking up from the atmosphere in this area makes it to the deep ocean, just for to put the numbers into perspective. However, as you can already see from the changing slopes in that upper panel, the accumulation rate per year is by no means constant throughout the time. It's highly variable, and what I show here is the decadal average accumulation rate of carbon in the deep ocean. And we see, tremendous variability from one decade to the next. But what I want to point out to you, and what I focus on mostly for the remainder of this talk and also in this paper, is really the very, very low accumulation rate in the last decade of the simulation, where the accumulation only amounts to 60% of the rate in the 1990s. But of course, if I compare to any decade in between, the decline in the attenuation is even more pronounced. So as a first thing to wonder is that this can be caused by two things. So it could either be caused by changes in the ocean carbon cycle or by changes in climate. So I first wanted to understand or get a better feeling for what actually causes this rather large variability over time. And for that, I turned to my simulation C. So again, to recap, that's the simulation with the constant climate and increasing CO2. So any variability, any changes you see here are only caused by changes in the ocean carbon cycle. The climate, the whole physical environment is kept constant at 1950s levels. So what we see here is that variability is a lot smaller than in our simulation A. So a lot of the variability we see in our simulation A is indeed caused by variability and change in climate. But most importantly is that the accumulation rates over time actually increase. So this is in stark contrast to the decline we see in the 2090s. So really there must be a change in the physical environment happening to really revert this signal that would just be caused by the increase in atmospheric CO2 to kind of result in this attenuation in the accumulation in the 2090s. So having said that, if you look at this, some of you might wonder, and we had extended discussions with our reviewers about this, the question, can we actually say that the 2090s are different from the preceding decades? Is this just a selected decade that just happens to be different in the context of this large decadal variability that I was just mentioning? So I hope to show you evidence from our model simulation that why we think that the ocean is actually in a different state in the 2090s in our simulations. So this is more than just decadal variability, but systematic change. So to assess this, I first applied a time series analysis tool that I would want to briefly introduce because I think it's a very, very cool tool. So this is the change point analysis. I'm not sure if any of you are familiar with this. It's a change point analysis. It's an R package to detect abrupt changes in climate time series. And I just have an example for you, like what this done. So let's look at this random time series. And I was just wondering, okay, is there any statistically significant changes in the mean and the trend? How do what statistical model do I fit to this time series? And of course, you can just go with, well, I can just fit a constant mean. I can just fit a constant linear trend, as it's often done, and say, well, this is the trend, this is the change in this variable in question over time. But then you could also say, but maybe there's a change in the trend. Maybe there is an abrupt change. Maybe there is a change point, a statistically significant change in the properties of the time series that shows up in such model fits. So what this package just does is just fits a number of different models. Big caveat, it's all linear models, but it's at its start. And I kind of let the package fit all of these models under some assumption with some parameters. But then I let the package tell me which of these models, objectively, statistically speaking, is the best fit. And here I use just the Akaike information criterion just to rank the models, and then this package will tell me which is the statistically best fit for any time series in question. So if we go back to our initial time series, the one up here, now translated into annual accumulation rates, you see there's tremendous variability. But then if we run the package, the change point analysis over this, we actually get the result that actually the linear trend with multiple change points seems to be the best model to fit this time series in question. And what I want to point out to you is that in the first half of the simulation, I drew the statistical model fits in blue in the back. We have increasing trends in accumulation in the first half of the simulation. And then if you disregard this peak here for a second, you have decreasing accumulation rates in the second half. There seems to be a systematic change in the background happening that is overlain by like about a 10-year phase of very high accumulation in the 2080s that I'll come back to in a second. So this tool can really, I marked now the change point and the direction of the trend on the x-axis here, can really give you at least some hint already that there is a systematic change happening in this time series, but there is more than just the systematic change going on. There's a lot of variability overlaying on this. So to dig deeper into the causes of this variability, I decomposed this into the contribution of biology and physics. So if we talk about the deep ocean carbon budget, of course, it could be biological particles sinking, biologically derived carbon sinking into this ocean volume that is somehow changing over time and or changes in the physical transport of carbon. So here I'm referring to, vertical and lateral advection, mixing, diffusion, all kinds of physical transport of carbon tracers. So here I'm plotting now the contribution of biology and physics on top. So biology in green, physics in blue. It's a bit hard to see if you look at the biological, the green line, but this is actually steadily increasing in contribution, but the increase is small, and there's no variability that resembles in any way the contribution of the physical fluxes to the total signal. So based on this, it's really the physics, the changes in the physical environment, the changes in the physical transport that cause the variability, and in particular the decline in the deep ocean carbon accumulation at the end of our time series. And in fact, the 2090s are the first decade where the physical transport actually does not act to accumulate carbon in the deep ocean, but instead acts to push carbon out of the deep ocean volume and bringing it into the upper ocean. So this is really not what we'd expect for this region where we think of carbon being transported down into the deep ocean in that area. So to decompose the physical signal even more, we've done a full deep ocean carbon budget of the physical fluxes. And I'm only going to show you vertical fluxes because they turn out to just dominate the signal in this area. And what I've done here now is to further decompose this area of interest into the slope, what I call the slope region in dark blue, and the open ocean region in light blue. So just to recap, it's the dark blue region where the newly formed dense waters would descend from the continental shelf and then kind of travel down along the continental slope in the southern Weddell Sea. So if I show you just, before showing you any bars, just want to point out the scale, the y-axis of these two contributions, so the vertical mixing and the vertical advection. We clearly see vertical mixing outweighs everything. So the vertical mixing is the dominant term here. And just for the sign convention, the bars that will pop up in just a second, any positive number denotes an increase in the deep ocean carbon inventory. So for the earlier part of my simulation, and I have to say that I only have this output for these 4 decades, so I only have start and end of the simulation, so I cannot do a full time series. But so for the first half of the simulation, first impression, we see all bars are positive. So we have an efficient downward transfer of carbon, both along the slope and in the open ocean, both via advection and mixing. However, if we move to the later part of the simulation, towards the very end, there is substantial changes happening. First of all, there's more and more negative bars, so an upward flux of carbon appearing in the system, consistent with the total signal that I've pointed out to you before. So really, the advective signal is entirely directed upwards in these latest 2 decades of my simulation. And for the mixing, this is also true as a net for the 2090s, but of course, the 2080s are actually dominated by this downward mixing event of carbon in the open ocean area. I want to point out this is not related to the transfer of dense waters along the slope. This is a different process that I didn't focus on too much, but this just points out to you, I mean, there can be individual events of open ocean convection also in this model, but this is kind of separated from the transport of carbon along the southern boundary along the slope here. So, but really what this tells me, this analysis told me then, is really that the decline, the variability and the decline in the downward transfer of carbon is caused by vertical fluxes, in particular the mixing. And this just implies that there must be substantial changes in the overlying water column and upstream on the continental shelf where the waters are coming from. So as a first step to assess this connectivity between the deep ocean and the upper ocean, we assessed an H tracer that we ran along with our simulations. So this H tracer can really be seen just as a proxy for ventilation, and it tracks the last water parcel's contact with any interface. Like it's not technically the surface. It doesn't have to be the atmosphere ocean surface, but it's also tracking the contact with the sea ice ocean interface or the ice shelf ocean interface. So it's a proxy for ventilation, but then also a proxy for just dense water formation. So these critical processes at these interfaces are kind of seen in these H tracer signal. So if we look at the distribution of this H tracer in the 1990s, and I've recalculated it to present like a ventilated fraction. So don't care about the numbers too much, just care about the color contrast. So we have the green representing poorly ventilated waters, so waters that are not in frequent contact with these ice ocean or atmosphere ocean interfaces, and then the purple waters that are very well ventilated and have frequent contact with these interfaces. And we see the expected pictures. So where it's shallow on the continental shelves, the bottom waters, which I'm showing here, are frequently in touch with waters that have seen the sea ice ocean, ice shelf ocean, or atmosphere ocean interface recently. Whereas, of course, the more we move into open ocean waters, this is less and less the case. And I showed two transects here on the sides. So one in the southern Weddell Sea and one in the northwestern Weddell Sea. And you can see that we have this purple whitish signal being communicated down. And the white isopycnals actually denote high-density isopycnals. So these really just illustrate that the bottom waters, the high-density bottom waters on the continental shelf are connected to the deep ocean in this 1990s setup. When we move to the 2090s, and here I'm now showing a difference in the age tracer between the 2 decades, we see a long blue tongue along the continental slope, if we look at the central map here. And this just really illustrates that these waters that sit there, the bottom waters sitting along the at the continental slope here, are way less well ventilated than they were in the 1990s. So really just illustrating this disconnect between bottom waters sitting along these pathways of dense water transfer and the waters that should supply them from upstream on the shelf. And secondly, if we look at the transects, these high-density isopycnals are not connected to the continental shelf sea anymore, just really further illustrating this disconnect that's happening there at the end of the 21st century. Really illustrating that the waters that descend from the continental shelves are not dense enough anymore to descend into the deep ocean. And of course, to assess this, we have to look at the density distributions and their changes. So for that, I start with an example transect in the southern Weddell Sea, going all the way from the ice shelf front, marked with the blue circle here, to the open ocean, marked by the black cross. And what you see here is a Hofmöller plot of the bottom density along this transect. So again, moving from the ice shelf front across the continental shelf break to the open ocean and over time along the x-axis. And what we see is that in the 1990s, or let's say the earlier part of the simulation, I would say, and it's maybe, well, it should be visible, bottom densities are more or less similar, at least. I don't want to say they're the same, but certainly they're in the same order of magnitude. So really, just showing that there is a potential of these waters sitting at the continental shelf to reach deep, at least in the open ocean offshore. However, as we move into the 21st century and towards the very end of the simulation, we see there's pronounced changes happening on the continental shelves, really illustrating this disconnect between bottom waters on the shelves and in the open ocean, where really these shelf bottom waters are substantially lighter than the bottom waters offshore. So, and coming back to this example time series that I've shown you in the beginning, what this actually showed is the time series of the density difference between this southernmost point and this northernmost point in this transect, and just the evolution of bottom density differences over time. And it turns out that this fit with the one change point in the 2070s is the best fit for this time series. So really, by the end of this time series, we're talking about bottom density differences exceeding 0.4 kilograms per cubic meter, which I would consider quite substantial. So these waters in this area turn from having denser waters, or at least as dense waters on the shelf as in the open ocean, to a system where the shelf bottom waters are substantially lighter than those in the open ocean. So, and most importantly, I think here is really there's an acceleration of this decoupling happening towards the very end of the simulation. Of course, this, yes, sure.
What's the rate of CO2 increase during this?
I mean, it's a high emission scenario. So yes, it's the SSP 585 scenario. So it goes all the way to, I think, 1200 ppm at the very end. So it's very, very rapid increase. Is exactly in those times.
So it's a really large.
Huh?
It's really large increase in CO2.
Yes, yes, it's substantial. This is probably like, yeah, we're pushing the system, absolutely, yeah.
Tell me what the vertical resolution of the ocean model?
Oh yes, of course. It's a Z level model. We have 99 Z levels. About 25 of those are below 2,000 meters, and the rest is above. Yeah, it's a lot of them, but yeah, it's not sigma. Yeah. Okay. So of course, this was just one transect cutting across the continental shelf, but now I wanted to see if that's actually representative for the whole southern shelf region there. And here I'm just showing this shelf break transect shown in the upper right in the 1990s. And you can see the colors, it's all green, doesn't matter. But what I want to point out to you is the hatching, which actually represents the presence of these precursors of inductive bottom water, so the Weddell Sea deep and the Weddell Sea bottom water in the 1990s. So we see these are widespread all across the continental shelf break there. So really large potential for these waters to then descend into the deep ocean. However, as we move towards the end of the 21st century, we do not only see blue everywhere, so that's a shift to lighter densities all across the shelf break. We also see that if we take the same temperature and salinity properties as in the 1990s, this area covered by these dense waters, as they were in the 1990s, really shrinks down to just a minor fraction of the shelf break. So really just showing that there's really a loss in potential of this shelf area to produce precursors of inductive bottom water that are deep enough to reach all the way into the abyss of the ocean. And to link that then to changes that actually happen on the continental shelf, we used a water mass transformation framework to really link the density distribution that we see locally to the surface buoyancy fluxes and their changes over time. And I'm only going to show you the total, the sea ice contribution, and the ice shelf contribution. So the E minus P and the heat contribution is an order of magnitude smaller, so I'll focus on the major components here. And I'll just briefly explain how to read this plot for those not familiar with this framework. So we plot the surface transformation in Sverdrup as a function of density. And anything that's positive here relates to or means a densification of the buoyancy flux in question of the waters. So sea ice in this area, as the light blue line, acts to densify waters, as we mostly have sea ice formation in the southern part of the Weddell Sea, and then the melting happens north of this region of interest. And then the ice shelves act to make the waters lighter by supplying meltwater. So in the 1990s, we actually have 5.4 Sverdrup of downwelling dense water, so that's the peak of this distribution. And that's actually in line with recent observation-based estimates. So the model does a reasonable job in producing the right amount of dense water in this area of interest. But then if we move to the 2090s, we first of all see also in this framework the decline in density. So we see the whole curve shift to the left on this plot. And this can be really attributed to a decline in sea ice formation, a substantial increase in ice shelf basal melt, of about 80%, and an overall increase in the heat content of the waters that sit on the continental shelf. I put the decline in magnitude of the formation of dense waters in gray here because I'm not showing this, but the control simulation actually shows a similar decline in the magnitude. So the shift in density is certainly the more robust feature than the decline in the magnitude. So this already brings me to a summary that we've seen in our high emission, admittedly very high emissions scenario. The deep ocean carbon accumulation in the southern Weddell Sea is attenuated in our model, and this sketch is just further illustrating the state as we think it currently works of the southern Weddell Sea in the 1990s with an efficient transfer of newly formed dense waters to the abyss, transporting carbon or drawing down the carbon as these waters sink into the abyss, whereas in the 2090s, we have the dense waters that are still formed at the same rates, but at much lighter densities, and just end up being too light to descend all the way into the abyss. So to answer this question that I posed in the beginning, are the 2090s really different? I would argue yes, because we do really have a system where the density distribution on the continental shelf is vastly different from what it was in the 1990s. Which is caused by changes in ice shelf basal melt, sea ice formation, and just heat fluxes. And these resulting dense waters are really just too light to reach the deep ocean, and thereby cause this attenuation and carbon sequestration. And with that, I'm at the end, and I take your questions.
Okay, thank you. So we have quite a few questions in the room, so we're going to start with those. And again, if you have a question and you're watching online, just go to Slido CGD seminar and we can take those. And I don't know who had their hand up first, so I'm just going to hand it to Keith and then you can pass it back when you complete your question.
Great talk, Cara. Thank you. I'm curious, what is the low resolution model missing? That because the process that you describe of the shelf waters getting lighter, and so they
Yep.
can't penetrate as deep into the abyss. It's not obvious that a low resolution model would fail to do that.
Well, I think it's my take on it. Not, I mean, my take on it is also how is the Antarctic slope front represented? So how can these changes in continental shelf processes be communicated to the open ocean? I think in my case, or in our case in this model, we have this correct dense water exit pathway at the bottom in the Filchner Trough, while having a very strong Antarctic slope front, which keeps the surface freshwaters actually on the shelf. So there's not much communication, I think, between the shelf seas and the open ocean and in the upper layers. The key processes happen at depth there.
Okay.
So it's really the exit pathway of dense waters, and at the same time, which I'm not talking about here, the on-shelf flow of warm deep water or circumpolar deep water. And it's the change in these processes, which are very local, very fine scale, that then ultimately control the fate, I guess, of the changes of the freshening or the shift to lighter densities.
Thank you.
Yeah.
Great. Thanks so much. So my question was about maybe the model setup. The water that's coming from the ice shelves, is that assumed to be basal melting?
Yeah.
Or does this allow for catastrophic ice shelf collapse?
No.
Do you
no,
think
no, no. It's a constant ice shelf geometry, so it's really just the basal melt.
Okay.
That we
then
have there. So
do you have any intuitions on how this might change if it accounted for?
Yeah, that's a good one.
Moving on.
No. It's yeah. I think we understand very little on what would change that, because of course, if we have a changed ice shelf geometry, that would impact the circulation under the ice shelf as well, like inflow, outflow of the cavity, maybe residence time in the cavity. So certainly a big impact. It would probably lead to acceleration of the ice shelf basal melt. So I would think we're on the conservative side by assuming constant ice shelf geometry. That would be my guess now, but yeah. Yeah.
Really nice talk. When you were showing the changes in ventilation from the 2090s
Yep.
to 1990s, the open ocean showed an increase in ventilation. So how do you explain that?
I think that's just a consequence of how this age tracer is set up. It's basically it's just an increase in age, in a way. That's at least my take on it. If this water does not, over time, this will see some ventilation, right? Yeah. The waters that sit, let's put it that way. The time it takes for the signal from the shelves to communicate, like to be communicated, so the signal of the purple waters in my left to communicate to the green areas offshore, it might just get there at the end of the simulation. So that what we see there is probably a result of what happened on the shelves, maybe, 50 years ago. It's very slowly creeping into the open ocean areas the further we move away from the slope. Because there we're really talking about the central gyre. That is hard to, this circulation would act to kind of almost go around it. So the ventilated signal would kind of be propagated around it. And it just takes much, much longer to reach that central part of the gyre. So I've always interpreted it as just being a natural result of just this ventilation kind of slowly, to some extent, propagating into the open ocean there. And this region not yet feeling the changes that happened, that are much quicker, more quickly communicated along the slope.
Okay, right. But if you had introduced your tracers earlier, if you had a simulation that extended back to 1900, for example,
Yeah.
I don't think you'd see an increase.
No, exactly.
In
I
those
think it's a
regions.
result of how we set up.
It's an artifact.
Yeah. Thanks for that question.
Okay, so we have Dan and then Peter.
Thanks for a really cool talk. I was wondering to what extent you think what you see in the 2090s is preconditioned by the huge event that you see in the 2080s, which presumably has impacts on vertical gradients of carbon and density, and then what the implications are based on that for internal variability in the timing of when you might see a reversal in fluxes, and also the persistence of this change beyond 2090.
So it's a great question. It's the obvious one, because so for the fade beyond 2100, it's kind of connected, I guess, to the rest. We have, unfortunately, I do not have forcing beyond 2100. So what we did in the review process was to run an extension with constant end-of-century conditions, just see if this just persists, and it does. So it's really, the occasional mixing event will still take place depending on what atmosphere we impose, if that causes the instabilities. But overall, the systematic change persists. I can actually calculate out the mixing contribution, and we see the systematic decline much more clearly, and I do that in the paper. Regarding your first, the mixing part of it, what I want to point out there, it's a very critical point, I think, also to look at in this model, because it does happen. It does not happen at the same regional, like spatial scale as in a lot of these CMIP models, but it does happen. And I cannot comment, unfortunately, on whether these events become more frequent. What I can say is they will leave a even more pronounced impact on the deep ocean carbon budget, simply because in this scenario, the upper ocean accumulates so much carbon that the profile actually, so when we think of the classical DIC gradient with lower DIC at the surface, higher DIC at the depth, not the case anymore at the very end. So any vertical instability that causes mixing on any time scale would leave a disproportionate impact on the deep ocean carbon budget. So it's, I think, very critical that we understand why these happen in these models and how much of that is realistic at it, because I think we don't have a good understanding of whether these even these smaller scale events are realistic or not, or just model artifacts. So, yeah.
Well, you've talked about quite a few of my questions. So what was so different in the 2080s from the 2090s? If you go back to look there, those plots where you showed the different
the bar plots?
Yeah.
So if we take the background state, so all these density changes that I've talked about, nothing is different in the 2080s. So it's really, this seems to be a systematic shift, a systematic decoupling of the continental shelf sea and the open ocean when we only talk about this transfer pathway of these dense waters to the deep ocean. However, this is overlain by instabilities that happen in the open ocean, away from this pathway of these newly formed dense waters, that have a magnitude to have the potential to just dominate any systematic change that's happening in the background. So there's nothing different in the 2080s per se. It's just an event that happens in the 2080s in the open ocean area that causes this spike in deep ocean carbon accumulation.
Did you study what that event was? I mean, that vertical mixing is at least twice as big as any other time during the run.
So I want to say I do not think that the mixing event itself, I haven't looked at it in too much detail, but I don't think that if I take away the carbon, it's actually stronger or longer than any mixing event I've seen before. The imprint is just more pronounced because I have higher carbon concentrations at the surface than I have at depth. So any strong vertical mixing event I have at this time of the simulation as opposed to 50, 80 years before that would just leave a much bigger imprint on the budget. Whether or not, I mean, that's also the region where we have the upwelling. So I mean, it's kind of course, this magnet just shows that the mix, it's so important to understand these open ocean processes as well at the same time as getting a better understanding of the shelf slope open ocean pathway, because they have the potential to dominate the whole budget.
Okay, final thing I was going to suggest was that you continue the run to see whether the 2090s were typical, and you said you've done that.
At least as best as I could with a constant. I mean, but I'm pretty confident based on this extension with constant end of century conditions that if we continued this scenario, I mean, no way this would go back to a system before, because basal melt rates, for example, accelerate also just at the very end of the simulation. There is a time lag between kind of the warming or the changes that happens for the waters in the ice-free, let's say, continental shelf area until that water reaches the ice shelf cavities. So there is feedbacks that I think are only beginning to kick in at the very end of this simulation. So I have no reason to believe that this would revert unless we drastically revert the warming and everything after the end of this scenario.
It's a bit of a follow-up to Peter's question. I just remembering your experimental protocol. Did you do an experiment with changing climate but not ramping CO2?
I did, but not in there.
Okay, because that
I have not.
would that bar disappear then with that explanation?
I would think so. But I unfortunately do not have the flux output to actually directly diagnose.
Okay.
Yeah, it's. But you're right. I mean, my hypothesis is yes, because if we look at the if we look at this one at the bottom here, so this is the constant climate varying CO2. And actually, if I look at the annual time series of this, there's very less spikes. So I'm thinking that there's no atmospheric CO2 increases in this one. So we have the gradient as in the simulation A, or the gradient change. But there's something about the changing environmental, like the physical environment, that causes more instabilities than in the constant climate condition. So something about the changing climate that causes this. But I have not looked in detail at what exactly.
Hi, Cara. I had a question about, you showed that like 2/3 of the increase in carbon sequestration was due to the physical processes, but then about 1/3 of it maybe was due to changes in biology. And just question, was that mostly due to the warmer temperatures and higher primary productivity, less sea ice blocking light? Could you comment on
all
that?
of the combined? so yeah, the increase in the biological contribution is actually, a lot of it is dominated by freeing up area. Like there's less sea ice in summer. So it's just offering a way bigger area for net primary production in the area. And at the same time having an increased gyre circulation, which brings up more nutrients from below. So it's kind of the combined impact of more nutrients, at least in the open ocean, and then a bigger shelf area that's actually ice-free in the summer. Yeah.
I was wondering if you could, so this is an uncoupled run.
Yes.
And so when you, my guess is that when you're shutting down some of these deep water formation processes, you're changing heat fluxes to the atmosphere that might not be reflected in atmospheric temperature. So could you comment on what the effects of that might be?
I cannot give you a number, but of course they will have a feedback. But I think because we're only seeing, I think the start of this decoupling really at the very end, it would be very interesting to have this run in a coupled setup and actually diagnose these feedbacks that are in place there, because that's the piece that we cannot answer with this setup. Yes, hi Nikki.
Hi, Cara. Can you tell us a little bit about what you're doing now that you're here in Boulder?
Yes, I'm moving back to. Yeah, I'm here one day a week. Yeah, that's what I do. No, but I'm working more in the open ocean again. That's moving a bit away from the shelves, or kind of connecting the two, I guess. So I'm working with Embass Ocean and their ability to have online or synthetic biogeochemical Argo floats. So we'll have a ton of Argo floats running along with our simulations that are measuring everything we want them to measure in our perfect little model world. And we can then kind of, look at spatial temporal variability in biogeochemical properties, carbon, nutrients, but then also look at sampling network design to kind of ask the questions, how many floats do we need and what region to represent aspect X or Y of the spatial temporal variability of any property you want, basically. So that's kind of spinning up in the background, that project. Yes. Yes.
Sorry, just one more question on this 2080s event. So
Yes.
you're just forcing with a single member from your fully coupled. So have you thought of, trying to
There's only
do
one.
multiple ensemble members?
Yeah, I would love to. For that specific, there's only one member for the SSP 585, so I did not have the choice for the 585. I would love to do that if I had more time computationally and just calendar. I have run different scenarios. So that was the priority, well, the route we took. But yes, you're absolutely right. It would have been great to have multiple. But I do think that the timing would have been impacted, but I do think the mechanism is robust because, for example, we do see that in the 370, we see the same mechanisms kicking in.
Same mechanisms
Not
giving
the
you that
280.
spike?
Well, again, I do not have the flex output for that either. It's kind of expensive to.
Right. I guess I'm asking, do you think that this is just internal variability and you just happen to have that? And
I think we have it in all of these. And it's just a matter of how pronounced they show up in this budget perspective, depending on what the vertical gradient in carbon then actually is at the time of any specific event. But it would be great to just only look at these mixing events and get a better understanding of frequency magnitude, what causes these, because I do think they're present in all of these, but just show up more pronounced in this particular case.
Okay. Oh, one more. All right.
I know you said you're doing something different now, but it would be interesting to take a look at this in a geoengineering scenario. So that's where your CO2 is going back down and see how if it reverses or if it is irreversible or whatever. So just food for thought.
Yeah, it is. When as a maybe a little add, I mean, I have a follow-up paper kind of in the pipeline. It just has 4 scenarios at least. So just look, it has the 1, 2, 6 in it, but it doesn't go high enough to actually push it, I think, far away to actually consider this a reversal scenario. But certainly, yeah, it would be great.
Okay, are there any other questions? We didn't have anybody put anything online, but quite a active conversation in the room, so thank you very much. And with that, let us thank Cara one more time for coming in.
Thank you.
Okay, and just quickly, we do have one more in-person seminar next week on the 6th, and then we are done for the fall 2022 season. Okay, so hopefully see you guys next week. Thanks.